Hi everybody, this is Jade Xu at the University of Memphis. In this video, we're going to learn how to conduct two-way ANOVA in SPSS. And this is the example we're going to use. The state superintendent wants to find out whether there's a gender difference in the scores on the standardized teacher examination for senior education student in 4 different majors. And the dependent variable, of course, is the scores on the test. And we have 2 independent variables. One is gender, and the other one is major. We have 4 different majors. So this is a 2x4 factorial design. I entered the data into SPSS. So gender have 2 values, 1 for male, 2 for female. And for major, the 4 different values are vocational education, physical education, English, and mathematics. Okay, in total we have 32 students in the sample. So to run two-way ANOVA, we come to this place, analyze, go to general linear model, and pick univariate because we only have 1 dependent variable. So here, put exam scores into the place for dependent variable and treat both independent variables as fixed factors. And in some cases, we're going to use, random factors as independent variables, but the difference between fixed and random factors is beyond the scope of our course. All right, at this point, you need to go to Options, Require Descriptive Statistics, Homogeneity Test, and Estimate of Effect Size. Now we click Continue and OK. Here comes the output of the two-way ANOVA analysis. In the first table, it just simply tells you that you have 16 male, 16 female students, and in each of the 4 majors, you have 8 students. And this is the descriptive statistics that provide you with information about the cell means. We have 8 cell means. And the marginal means, remember we have 6 marginal means. So this is a marginal mean for male student. This is a marginal mean for female student. And those 4 are the marginal means for major. And this is the grand mean. And for each of the mean, you have the corresponding standard deviation, and the size of the particular groups give you a hint whether it's a cell mean, or marginal mean, or grand mean. Remember, we have the same 3 underlying assumptions for t-tests for one-way ANOVA and two-way ANOVA. And the one we always test is the homogeneity variance assumption. So here we're going to look at this test, the test of equal variance, see if we meet the assumption of homogeneity variance. Since this test, the F-test has a p-value of 0.248, which is greater than our alpha equals 0.05. We fail to reject the null hypothesis. In other words, we met the assumption of homogeneity variance. That's good news. We do want to meet this assumption before we run ANOVA test. And here is a table for ANOVA, two-way ANOVA. It's not titled like that, but that is where we have answers for the 3 hypotheses we specified at the very beginning. So remember, we have for gender as the first independent variable. The null hypothesis, the average mean of male and female students do not differ significantly. And for the second independent variable major, the null hypothesis, the average scores of students in the 4 majors do not have significant difference. And in addition to the test of the 2 main effects, we also have a test for their interaction effect. And here is the hypothesis. In this table, we first remember we need to ignore 3 lines. Ignore the first line, that's corrected total model. Ignore the second line, that's the intercept. And ignore the line, the second to the bottom, that's total. Okay, cross out those 3 lines. And here the line for gender is the test whether there's difference between the 2 groups. So if you have the sum square, it's right here, 0.281, the degree of freedom, we have 2 groups less 1, that's give you degree equals 1, degree of freedom equals 1. And the ratio of the 2 is the mean square. The F test is the mean square of this variable over the mean square of error. Given the F value of 0.028, the chance for us to observe the mean difference between the 2 groups, which is 35.81 versus 36, almost no difference. What's the chance for us to observe this difference if the null hypothesis were true? It's 0.686, so greater than 0.05. We fail to reject the null hypothesis and come to the conclusion that there's no significant difference in the average scores of male and female students on the test, given alpha equals 0.05. Now move on to the next variable. We have the second independent variable, which is the major. We have 4 majors, so the degree of freedom is 3. Sum square divided by degree of freedom gave the mean square. This mean square of major over the mean square within, or the mean square error, you have the observed F test, almost 16. If the null hypothesis were true, the chance for us to observe such a strong difference between the 4 majors, this average score of vocational education is as low as 30, and the average score of student in mathematics is as high as almost 41. The chance for us to observe such strong difference is lower than 0.001. So we reject the null hypothesis and come to the conclusion that there are significant differences in the average score of students in the 4 majors. We're not done yet because we know there are 4 majors, we know they have significant difference, but where are the differences exactly? So we have to do post hoc pairwise comparisons for this main effect. Okay, before we run that, let's take a look at the interaction effect. That's our third hypothesis. And the sum squares divided by its degree of freedom, we have a mean square for the interaction effect 30.365. This mean square divided by the mean square error 9.99, we have a F observed value 3.04. If there were no interaction effect, the probability for us to observe this F value is lower than 0.05. So since P is lower than 0.05, we're going to reject the null hypothesis and conclude that there is a significant interaction between gender and major in this particular study. When we identified a significant interaction effect between the 2 independent variables, we need to conduct something called the test of simple effect to pinpoint where are the differences between the cell means as a post hoc test following a significant interaction effect. Before we move on and learn how to do the post-hoc test for major and how to do the test of simple effect for their interaction, I want you also pay attention to this column, the partial eta squared. This is the way to estimate effect size offered by SPSS. You can see that gender explains almost nothing of the variance in the dependent variable. In contrast, major explained about 67% of the total variation in the scores. Also, the interaction between gender and major explained about 28%, 27.5% of the variance in the dependent variable. Since we got a significant F ratio for major, and as the main effect it has more than 2 levels, now we need to do a post-hoc test for that particular variable. So we go to the same place we did our two-way ANOVA, but this time we come to this place called post-hoc. And remember, we want to do the test for major. And since we met the assumption of homogeneity variance, we have equal group size. We can choose 2 key as the post-hoc pairwise comparison procedure. Continue. You don't have to change anything else. Just click OK. Remember, this is what we need to do to get the post-hoc pairwise comparison following a significant main effect that has more than 2 levels. We've already seen the first part of the output as the initial two-way ANOVA analysis. And this is the part we need to pay attention to. This is a post-hoc test for major, as shown right here. And as all other post-hoc, we have half of the table as redundant information. And we need to pay attention to here. The sig column, that's the probability value. You compare the p-value here with your alpha level. It's clear that there is a significant difference between the average scores of students in vocational education versus physical education because the p-value is lower than 0.05. And students in vocational education also have a significant lower score than those in English major. And they also have significant lower score than those in mathematics. Another pair that also have significant difference is between physical education and mathematics. The 2 pairs that do not have significant difference, one is between physical education and English, the p-value is 3.365, and between English and mathematics, the p-value is 0.289. You can see in this table, vocational education as group is significantly different from all other 3. That's why there's no other means listed in this column. Where for physical education and English, they are homogeneous subset, so are the English and mathematics students. Okay, so this part we have right here is the post-hoc test for major as a main effect. And I am going to show you how to conduct the test of simple effects in a separate video.